I'm Haley Bowden. I'm a graduate student working with Peter Bruzzi at University of Arizona, and super excited to be here and talk to you guys. So I, like many of you, am interested in what the physics that drives the great diversity of galaxy properties we see, and in particular, I'm interested in how the properties of the galaxy's host halo influence that. Unfortunately, sometimes what I want to observe is this, and what we see instead is the galaxies. The problem that I'm trying to solve is how do we learn the mapping between halo properties and the galaxies that we observe? We have a simulation or a forward model that can take us from this space. Here in particular, I'm concerned with halo masses, concentrations, and accretion rates. And we can go from that space and forward model to observables. It's a little bit more challenging to go the other direction confidently and look at an observation and say this is the properties of the host halo of that galaxy. But simulation-based inference provides us a way to do that. But first, we have to have a forward model. So in this case, I use Universe Machine as my way to go from the dark matter only simulation to a galaxy catalog, and in particular to forward model observables. And so here's the basic idea of what we're trying to do is to learn the probability of halo properties given an observation X. And all we need is a simple prior on halo properties and the likelihood that a given observation would give us, halo properties would give us that observation. Now this likelihood can be very simple in some cases. So for example, if we just wanted to know the halo mass given the stellar mass of the object, I'm not claiming that stellar mass is an observable, but we're going to treat it as one for right now. If we know stellar mass with some small degree of uncertainty, we can get a posterior on our halo mass fairly straightforward from just this. Now, of course, there's other information that might be helpful in making this. So if you've heard me talk here a couple years ago, I talked about using, is the galaxy isolated? Is it the brightest cluster member? Is it a satellite in that cluster? All of that information can help us get more accurate constraints on halo mass. So particularly at the high mass end. This problem gets a little bit less tractable when we go to secondary halo properties. So if we wanted to look at concentration, and again, we just use the stellar mass, well, we might be looking at the wrong property, probably, of the galaxy. But it also might be that the link between our observables and our halo property is a more complicated mapping than when we had our stellar mass-halo mass relation. So, for example, one source of information that we might want on concentration is we might use the assembly bias to tell us about this. So this is, what you're looking at right now is the correlation function for all of the halos in my simulation box. And if we select just the half of halos that have the lowest, lower half of concentration, we get a less clustering. Similarly, if we do high concentration. And this is also true if we look at other secondary halo properties, including accretion rate, and the signal is distinct between these different properties. So we're getting different information from the signal for all of them. So we still have this problem. We want to understand the halos, but we're observing the galaxies. The halo assembly bias gives us some clues. The properties of the halo via the galaxy halo connection give us other clues. And so how do we learn this mapping? We have our, in this case, I'm using just a very simple, let's just use the stellar masses of these objects, or like an observationally derived stellar mass, the projected separations to the 5 nearest neighbors, and the line of sight velocity separations. I can compress all of that into an input vector, and then I use simulation-based inference, in this case a neural density estimator, to get from that input vector to these probability distributions. So the way that this works is basically I have my simple prior on my halo properties. This is basically just the distribution of the halo properties in my simulation box, and I'm trying to learn the transformation that takes me from that prior to my posterior. And this transformation is that likelihood. And the way that I learn this is by with the network, taking observations, going, is this compatible with this halo property? Does this combination of halo properties give compatible or incompatible results? So here's an example of this applied. You can see this is just one galaxy. We have halo mass, concentration, and specific accretion rate predictions. And in white, you see the true value. In orange is the full distribution of the properties in the simulation box, and in blue is the predicted posterior. So looking at a larger sample, here we've just taken the median and standard deviation of these distributions to get the predicted versus true halo mass, concentration, and accretion rate. And this is very faint, sorry. But you can see that there's a pretty strong signal across all of them. It's strongest in halo mass, of course, as in the standard deviation is tightest in the halo mass, but there is a signal across all of them. Now, the question remains, can we trust these posteriors? And this is a question that a lot of people doing simulation-based inference have come up with many different ways to try to test whether your posteriors are an accurate depiction of the actual likelihood. One way that you might not have heard of is to use Bayesian deep learning. So in most cases, the standard is to train your neural network with some kind of gradient descent algorithm. You're minimizing the likelihood. You know what I mean. And in this case, we can instead use MCMC sampling, where the weights and biases that make up our network are parameters. We're sampling over this space until we reach convergence. And in particular, I am using a sampler that my advisor, Peter Baruzzi, has been developing called a ray tracer. And this is like a Hamiltonian Monte Carlo, except instead you have a ray, you are tracing the path of a ray of light through a medium of varying index of refraction, where that index of refraction reflects your likelihood. And the great thing about this version of sampling is that it works very well over a super large parameter space. So I can have a network with thousands of weights and biases and still reach convergence very quickly. So here you just see a example where I'm running this ray tracing sampler. There's going to be a bit of a burn-in period, but then what this tells me is about the stability of my predicted posteriors and how much they vary as you change the weights and biases of the network. And so I'll just leave with my summary then. I am trying to figure out how to get the likelihood of halo properties of observed galaxies, and that it is a work in progress, but I'm happy to hear any suggestions or questions anyone has. Thank you.
Hey, that's very nice, thank you. You've shown marginalized posteriors there, but I guess you're predicting the three, so a multidimensional posterior distribution.
Mm-hmm.
So I guess there are plenty degeneracies there, right, into between mass concentration. So all of them are related.
Yes.
So I was wondering if you have looked into that and.
Yes, so they are fairly degenerate. The reason we moved into the specific accretion rate rather than just the accretion rate was to try to reduce that a bit. But yes, no, I haven't looked into that in great detail.
Thank you.
The young people get a chance to ask. I was curious whether you might subject your methodology to much more finer radial properties of the halos, because we found Sandy and I working with Bolshoi, for example, that you just get this global thing, RV, et cetera. But we'd love to know what's happening at, let's say, 1/10 RV or 1/2 RV, et cetera. And that would, of course, increase total parameter space huge, because you have that R dependence as well. Is that something that you can explore? Is that beyond the reach of the compute power, et cetera, to have finer divisions of halo properties?
Yeah,
that's much closer tied to galaxies, which are at the bottom of potential, real halo.
Yeah, that's a really interesting question that I haven't considered. It's definitely something that that isn't out of the range of what this method could do. Yeah, I would have to think more about what the practical implications of that would be. But yeah, that's an interesting suggestion.
Okay, let's thank Haley again.